Hello. What we're going to study in today's video is continuity. And you know a good bit about continuity already. So first of all, we can tell that these graphs are continuous. Real simple, because we can trace them without lifting our pen. Okay? Both of them we can trace without lifting our pen. That's like the simple way to think of continuity. When we think about discontinuity, basically we cannot trace a function without lifting up our pen. And there are three kinds of discontinuity. The first one that I'm showing you here in f of x is called infinite discontinuity at x equals 0, because what we have is that the left and right side of this rational function are approaching an asymptote at x equals 0. So it's continuous from negative infinity to 0, and then again from 0 to infinity, and notice that we have parentheses here because it is not continuous at 0. We don't even have a point there. The second kind of discontinuity is jump discontinuity. So from negative infinity until 2, it's continuous, and then from 2 to infinity, it is continuous. What happens at 2 is we have a point of discontinuity, and that's what makes it discontinuous. So it's continuous from negative infinity to 2, and then from 2 to infinity. And I'll show you right here how it's written with the parentheses again because the 2 is not included. The third graph is an example of jump discontinuity. So we're continuous from negative infinity to 1, and then we jump down here from 1 to infinity. We are continuous, but it is discontinuous at x equals 1. And notice that even though we have a point here, we don't include it as being continuous because there's nothing to the left of it. So everything starts right there. What I want you to look at for the second example, and this is where we're going to really get into some new material, is that another way to think of this is, that the limit as we approach 2, okay, the limit as we approach 2 is not equal to f of 2. Okay, so the limit of the function as x approaches 2 is not equal to f of 2, meaning the height of the point when x is 2. So let's go to the next page. And we're basically going to have a 3-step process each time to determine whether a function is continuous or not at a given x value. So 3 things we're going to do. First off, is f of x defined at that x value? In other words, is there even a point at whatever x value we're working with? The second test is to see if there's a limit as x approaches that particular value of the function. Okay, so in other words, is there something like this going on? Yes, then we would say the limit does exist when x equals a. Or, that shouldn't really be that. Is something like this happening where the limit would not exist at that particular x value? So if those two are true, if there is a defined point at f of x and the limit as x approaches our particular value exists, then what we want to see is, does the limit at that x value equal the height of that point? Okay, so let's go through and let's do a couple of examples. So example 1 says, let's find where the function is continuous. And I'm giving you this function for all x values not equal to 1. Well, I would imagine you're looking at this and you're saying, hey, I can factor that. So let's factor this. And we know x can't equal 1 because that would give us 0 in the denominator. But look what happens. Okay, we get x plus 3. And what we know about that, if we were to graph this, just graphing f of x equals x plus 3, let me write that down. Okay, that is a line that has a y-intercept of 3 and a slope of 1. Now, we already said there's not going to be a point at x equals 1, and in fact, you should know that this means there's a point of discontinuity. So let's figure out where is that point of discontinuity. Well, x minus 1 equals 0, x equals 1, and then if we drop the 1 into what's left, we have a pod, point of discontinuity, at 1, 4. So I'm going to go drop that onto my graph right now. Okay, so that's our point of discontinuity, and then when we graph the function, it's basically going to look like this. So that's what our function looks like. So what we can say to answer this, let's find where a function is continuous. It is continuous from negative infinity to 1, not including the 1, and union 1 to infinity. Okay, so the only place it's not continuous is when x equals 1. But there's something interesting about the points of discontinuity. We actually call a point of discontinuity removable discontinuity. So that is a removable discontinuity. The reason it's removable is if we just put a point there, we no longer have a discontinuous graph. So we found out where our pod was, which is at 1, 4. So to make it continuous, if we just said, hey, when x equals 1, make the height 4, we're basically placing a point right here to fill in the gap so that it would no longer be discontinuous. Now, I want you to understand, we cannot do this for infinite discontinuity, because with infinite discontinuity, say we have something like this, we can't just put a point here because it still wouldn't be continuous. This is going to infinity, this is going to negative infinity. No way to just drop a point in there, keep it as a function, and make it discontinuous. Or I'm sorry, make it continuous. The same goes for jump discontinuity. If we had a function that went like this, and then we had another function that went like this, there's no point, there's nothing we can do here that would make this continuous without making it so it wasn't a function anymore. So a point of discontinuity is the only kind of removable discontinuity that we will have. Okay, so let's take a look. Okay, you're going to try this one. I want you to find where the function is continuous for all values where x does not equal negative 2. So I know what you're thinking. You're like, yes, I get to factor. So hopefully you factor that out. Okay. If we were to graph this now at x, we have x plus 5. So 1, 2, 3, 4, 5 is our y-intercept. Okay. And this also has a slope of 1 like the previous. But in this case, at 2, we're going to have some kind of discontinuity. And just like we had on the previous example, because we have x plus 2 over x plus 2, we're going to have a point of discontinuity. So we would solve and we would get negative 2. Oops, what did I do? It should have been over here at negative 2. I'm so sorry. At negative 2. Whoops. When we put our negative 2 into what remains, once we simplify that, we get a height of 3. So at negative 2, 1, 2, 3, we will have a point of discontinuity. Graphing the rest of this, which leaves us with x plus 5, we will have a line that looks like this. But of course, we have that gap right there. So our pod is at negative 2, 3. So in order to make this continuous, we would just say when x equals negative 2, let y equal 3. Okay? As it stands, if we were not to have filled this in, we would say that it is continuous from negative infinity to negative 2, union negative 2 to infinity. Okay? So only when there's a pod, if we ask you, hey, how can we make this continuous? You would say, well, put a point there. basically fill in the point of discontinuity. Okay, let's take a look at these functions. So we have the function y equal, or f of x equals 1 over x squared. So just looking at this, as x approaches 0, we know we can't have a 0 here. Okay, but let's put some numbers in. Let's put in like 1. Well, 1 over 1 is 1 squared. How about 2? We'd get 1/4, 1/9, 1/25, and so on. Function is going to look like this. It's a rational function. And on the other side, it's going to do the same thing. So, looking at this, what I hope you know is this is not a removable discontinuity because we have an asymptote at x equals 0. So we say this is a non-removable discontinuity. Okay. For the next one, we have the limit as x approaches 0 of the cosine of 1 over x also does not exist. If we drop the 0 in here, we have 1 over 0. It is undefined. This is an interesting one because if you were to graph this function, it's kind of a little chaotic as we get in here. And the same thing from the right side, it starts to get chaotic in here. And we have our point of, or we have a little discontinuity right there. X cannot be 0. Okay, we can't drop a point in there. Okay, so this is not an asymptote, but it is also a discontinuity. Okay. Oh, absolute value. Don't we love our absolute value? So I'm asking you to take a look at this graph and determine if this kind of discontinuity is removable or not. What kind of discontinuity do we have? So I've done the workout for you. I mean, we should know how to do absolute values by now. If we were to look at this as x approaches 7, 1, 2, 3, 4, 5, 6, 7, we have from the left, the limit approaches -1. We know it looks like this. And from the right, the limit approaches 1. Notice those are both open circles. So I'm going to say a couple things. First of all, f of 7 does not exist. So it's going to be discontinuous. And the limit from the left and the limit from the right are not equal. We have jump discontinuity here. So this is not removable. Okay, it is not removable. It's jump discontinuity. Okay, example 4. I love these problems. So example 4 says, for what value of c, okay, so for what value of c is the function continuous on the interval from -infinity to infinity? So I know I have it over here, but what we do is we set these two values equal to each other after we substitute the 3's in for x. So I'm going to substitute the 3 because we're going from less than or equal to 3, that's the left side, and greater than 3. So let's substitute the 3 in for x. What we get is 3c plus 1. And in order for this to be continuous, the left side and the right side must both be approaching the same height. So we're going to set that equal to, going to drop the 3 in here, 3 squared is 9. So 9c minus 1. And then we're going to solve. So subtract the 3c, we get 6c. Add the 1, we get 2. Divide by 6, divide by 6, we get c equals 1/3. So the only way, the only value that would make this piecewise function continuous from -infinity to infinity is if we put a 1/3 in here for c. Okay. I know I went through that quickly, but I'd like for you to pause the video and see what you can do. Okay, I want you to try to find what value of c would make this piecewise function continuous, noticing that the break is at 4. So go ahead and pause this video, see what you can do. So I kind of skipped over this part before, but what we're really doing is doing the left-sided and right-sided limits. Okay, so that's what I have here. The limit as x approaches 4 from the left, so that's what we're doing when we're substituting the 4 in here. And then the right-sided limit, we're substituting the 4 in here. So now what we need is we need for the left-sided limit and the right-sided limit to equal each other, which is why we will set 16 minus c squared equal to 4c plus 20. Now, hopefully you notice this is a second degree, so we're going to have to set everything equal to 0. So I'll add the c squared over, keep the 4c there, subtract the 16, plus, and now factor and solve. C plus 2 times c plus 2, which means the only c value that will make this function continuous is if c is negative 2. Anything other than that would create a jump discontinuity here. Okay, so that's the only one that would make it continuous. So that brings us to a little word problem. Okay, so we're talking about state income tax codes. We're looking at, we want to make sure the functions, we want to figure out they're discontinuous, okay, at x equals a. And what we want to do is we want to figure out what value of c would make them continuous. So what we're going to do is we're going to set the left-sided limits and the right-sided limits equal to each other. Now we have a couple of breaks here. We have a break at x equals 0, and we have a break at 10,000. Okay, so take a look at what we have here. So we're taking the limit of the function as, first of all, the limit at x equals 0. If you make no money, you pay no taxes, right? So that, there's nothing to do there. But the limit as x approaches 10,000 from the left, it has to equal the limit as x approaches 10,000 from the right. Okay, so that's what we're going to look at. So from the left, if we put 10,000 in here, we get 1,400. From the right, if we put 10,000 in for x, we get 2,100, c plus 2,100, right? So now we'll set those two equal to each other and solve. Our c value would be negative 700. So that's what's going to make our function continuous. Now, why should paying taxes, why should that be continuous? Well, if you think about it, if you made less than $10,000 and you paid a certain amount in taxes, that shouldn't jump up drastically just because you made maybe 1 cent more and you made $10,000. It should be continuous. Okay, so it shouldn't be that, oh, I made 1 penny more and now I have to pay a bunch more taxes. No, no, no. We want that to be continuous. Okay, so hopefully this was helpful. I know I went through it quickly, but I think you got it. Have a great day, everybody.